Hi everyone. Today's topic is continuous Chapter 7, continuous probability distribution. Okay. So in this chapter, I will discuss the normal distribution, which is very important in chapter 8 and 9. Okay, in chapter 6, we learned about the probability model and based on the discrete random variable. So in the discrete random variable, usually based on the counting something. So that is always the number of customer arrivals in the next minute or something like that. But in this chapter, we will study the continuous random variable. It is not countable, but it is, for example, if we would like to model that the waiting time until the next customer will arrive, so then it is not represented by one single value. So in this case, we have to use that continuous random variable. So continuous random variable can have a non-integer decimal values. So usually the discrete variable has not always, but 99% of the discrete variable may have the integer value, but continuous random variable has can have all the real numbers. So if you want to discrete random variable, we can define the probability of one point and the probability that it is x is discrete random variable, then probability that x is less than 2, then we can obtain this probability of 0, probability of 1, and probability of 2. But if x is continuous variable, then this probability for one point is 0. So instead of using the probability of one point, the continuous random variable use the probability density function. So we cannot say that probability that x is exactly 54. So this probability is 0 mathematically. But in continuous random variable, x is continuous random variable, then this probability is 0. But the probability that these random variables lie on this interval greater than 53.3, less than 54.5, 53.5 to 54.5 is some value. This probability has a value larger than 0. Of course, it should be less than 1. Or the probability that x is less than 54, or probability that x is greater than 53. So this kind of thing has a value, but so all the continuous random variable can be defined by this method. So this kind of expression is nonsense in continuous random variable. So in discrete random variable, we may have a domain as 0, 1, 2, 3, 4, 5, something like that. But in continuous variable, we can define, so in discrete variable, we can consider that x is 0, so this kind of expression is meaningful. But in continuous variable, the probability that x is same as 54 is always 0, so it is not interesting. but probability that x is between this interval, it has some value between 0 and 1. So x is between 53.5, 54.5, so this one has some meaningful value. So continuous random variable is so difficult to see directly. So the probability of x has some value is not directly observed. It is not directly observed. So we have to consider that x is included in some interval. So it is interval. So of course, the probability density function, probability distribution function of discrete random variable is very important. And we studied the binomial random variable, probability density function of binomial random variable. That is very important. But in the continuous random variable, probability distribution function is more important than the discrete random variable. So all the continuous random variable can be defined by the probability density function, PDF, and the cumulative distribution function, CDF. Okay? So the probability density function must be non-negative, and area under the entire PDF must be 1. So, and we denote that probability density function as small f. And mean and variance and shape can be depends on the probability density function. And cumulative distribution function is actually cumulative distribution function is nothing but probability that x is less than I'm sorry, or equal to small x. So here is x. Okay. Yeah. So cumulative distribution function is also very important issue. But if we know the probability density function, then cumulative distribution function can be obtained by this equation. Okay. For example, figure 7.2 is so example of probability density function. It is normal distributed probability density function, and it is cumulative distribution function. Cumulative distribution function. Okay. So normal case, okay, yeah. If we integral this distribution from minus infinite to plus infinite, then this area is become 1. The size of this area is 1, and so cumulative distribution function is so. For example, if you want to know that this cumulative distribution function, it is f for 70, so then that means here is 70, here is 70. The area less than 70, so this area, the size of this area, value of this area is this number. So this number is this one. So that is the size of this area less than 70 is the cumulative distribution function for 70. Okay. So the same way. So that's why cumulative distribution function is increasing, strictly increasing function, because if you take the f65, then the area is here. But if you take the 70, then area is increasing, value of area is increasing. 75, then area is increasing. So it is increasing function. Okay. So then, if you want to know that probability of continuous random variable x between a and b, then it can be obtained by the size of area between a and b. This size of this area is probability that x is between a and b. So then how can we calculate this size? So probability that a is greater than x less than b. How can we calculate this probability? It can be calculated by the integral a to b fx dx. So that is the way to calculate the area between a and b. But this integral is so difficult. So for your level, but many mathematicians can calculate it, but you are not mathematicians. So we have to use another way. So we can use the Excel, or so in normal case we can use some table. We will discuss how can we calculate it for the normal distribution later. Okay, and so this probability, if x is continuous, if x is discrete, then it is different. If x is continuous, then probability that x is equal to a is 0. Yeah. So because of this property, the probability that x is, probability that a greater than or equal to x less than or equal to b is the same as probability that a strictly greater than, so less than x and less than b. It should be less than. Okay. So again, probability that x is greater than a and x is less than b or equal, so greater than or equal to x, a is less than or equal to x, b is greater than or equal to x. So, and here we don't have equality, but this two probability is the same whenever, so this equality is not big deal, it is not important. So we can remove this equality property. So we can remove, but the probability of these two expression is the same. So probability that, so this x is between a and b and it has equality, then it is the same as probability that x is strictly greater than a and strictly less than b. So this probability and this probability is the same. Okay? Because of this fact, it is true only for the continuous random variable. If your random variable is discrete, then it is different. But x is continuous, then these two expression is exactly same. So then, based on the continuous random variable, how can we calculate expected value and variance? So it is given by this equation, integral. Okay. So in mean case, in discrete case, we calculate mean of x using discrete random variable. In discrete random variable, we use this expression I is 1 to n. So we just change this summation sigma notation to integral, then and xi to x continuous, and probability of xi is the PDF times dx. Then that is the expression for the mean. So mathematically it is defined like this, but in this statistic course, I know you are not mathematicians and you're weak for mathematics. So I do not ask you to take the integral of fx dx. So instead, we can use many properties of the normal distribution. And variance is given by sigma square, but you have to know this expression. So otherwise, you cannot say that you're studied the statistics. Okay, so that is again integral minus infinity to infinite x minus mean, x minus expected value square, and probability density function dx. So that is the equation for the variance. And we will study the continuous random variable one by one, but so let's pass the uniform distribution because it is so simple. Let's study the normal distribution in this chapter. So and we can study the exponential distribution, but it is it is not so important in this course. But if you have any chance, then you can study the exponential random variable. But in this summer course, in this online course, let's study only the normal distribution, which is most important continuous distribution in the world. If you understand the normal distribution, then you can study the other continuous random variable by yourself. For example, we will discuss t distribution later, but don't worry, I will teach you. Okay, so this normal distribution has another name, Gaussian distribution, because this normal distribution is first introduced by the German mathematician Karl Gauss. So many students ask me that so normal distribution and Gaussian distribution, whether the normal distribution and Gaussian distribution is same or not. But it is exactly same. Gaussian distribution is normal distribution and normal distribution is Gaussian distribution. Okay, so normal distribution or Gaussian distribution also given by it is continuous random variable, continuous distribution and distribution for the continuous random variable, and it has two parameters mu and sigma. So if one random variable x is normally distributed random variable, then we denote it by normally distributed, so we say normally distributed n normal, and mu and sigma. So we have two parameters to define the normal distribution. Okay. So the probability density function of normal distribution is here. So probability density function of normal distribution is 1 over sigma square root 2 pi e exponential minus 1 over 2 x minus mu divided by sigma square. So this sigma and this mu are parameter, so it is free, and here sigma is free, and x is this x variable, and e is exponential function, and pi is the pi. Okay, so pi is the pi 3.14. And e is the exponential function, or it is approximately 2.718. Okay, and so we denote it by n, mu, and sigma. Very important fact of normal distribution is that expected value of normal distribution and normal random variable is mu, and variance is sigma square. That means if we calculate integral minus infinite to infinite x fx dx, so that is integral minus infinite to infinite x times 1 over sigma square root 2 pi e to the minus 1 over 2 x minus mu divided by sigma square dx, then it becomes mu. So the details are omitted because you need not know the details. And sigma, so variance of x, which is integral minus infinite to infinite x minus mu square 1 over sigma square root 2 pi e to the minus 1 over 2 x minus mu divided by sigma square dx is sigma square. Okay? So if we apply the equation mean and variance for f, so the f is PDF of, if we apply the PDF of Gaussian distribution, 2 pi e to the minus 1 over 2 x minus mu divided by sigma square. If we put this equation into here and here, so then mean of x become mu and variance of x becomes sigma square. So, okay. Yeah. So mean, mu, and standard deviation sigma is sometimes denoted by this one, normal distribution. Okay. So domain is minus infinite to plus infinite. Mu is mean, sigma is standard deviation, and mu and sigma is mean and standard deviation, and shape is symmetric. So, and mesocortex, so you need not to worry about it. So bell shape. Okay, so in Excel, you can use this equation. So if we have so 0, then it is probability density function. If you want to calculate the cumulative distribution function, then it is x. 1, I'm sorry. Okay. So the probability density function is, the shape of probability density function looks like that. 1 over sigma square root 2 pi e to the minus 1 over 2 x minus mu sigma square is, this function looks like this bell shape and symmetric. And the cumulative distribution function is very so lazy S shape. So that is integral minus infinite. So it is fx. So fx is given by this equation. Fx in this case fy dy. So whatever it is, so cumulative distribution function is this shape. Okay? So they say the range S shape. Okay. So the normal distribution has very similar, same general shape. Okay? So, for example, if you have considered two normal distribution, one is mean 42.70 and standard deviation is 0.01 and normal distribution, that is one normal distribution. And another normal distribution is mean 70 and standard deviation 10, 70 and 10. So then here is a real number, and here is 70, and here is 42, 42.70 in previous one. So then, and this random variable normal distribution 70 and 10 has standard deviation 10. So the bell shape is like this. And this normal distribution, it is actually n 70.10. And let's consider that n 42.7, comma 0.01. So then it is normal distribution, so it has this shape because the standard deviation is very small. It's 0.0701. It's very small, so this random variable looks like this, and this random variable looks like that. 0.01. But if you draw this random variable into this square window, then you have this shape. Okay? And if you draw this normal distribution to this square shape, so here is 42.70, and here is 42.667, so 42.67, so here to here. So then we have to increase this interval to fit here. Okay, we extend this interval to fit here. Then everything is scaled. So this shape is scaled on here. It is zoom in. So then this shape, if we change the scale, then this bell shape and this bell shape is very similar. Okay? So if you change the scale, then all the normal distribution has the same shape. But if you just preserve this scale, so it is 0.01, 0.01 standard deviation. So standard deviation is scale factor. So 10 is scale factor. If 10 is scale factor 10, then it is extended. And so if the scale factor is 0.01, then it has very high thickness. But if you change this scale to this big window, then the shape is exactly the same as this one. Okay? So that is very important property of normal distribution, and usually they say that it is self-similarity. So, that is very good property. So, we can consider the standard normal distribution. If we change, here is 42.70, and our distribution looks like this. So that is normal distribution 42.7, 0.01. So that has very high thickness. And if you move this random variable to 0, so then it is x. Then we change this x to here, then we obtain that x minus mu. So mu is 42.70. So then we have, so again, so here is the real number, and we have very high peak random, the 42 distribution 70, so it is normal distribution 42.70, 0.01, and if you change it to here, so it is x minus mu, so it is mu is actually 42.70, then we can change this distribution to here. So it is normal distribution. So it is we take this one. So mean becomes 0, and standard deviation is still 0.01. After then we divide it by sigma. So in this case, sigma is 0.01. So then, if we divide it by 0.01, then that is the same as x minus mu times 100, because divided by 0.01, then it is the multiplication. So then it is 100%, 100 so times larger than the original distribution. Here is 0.01, but it becomes that 1. Okay, so it is enlarged. So then this new distribution has normal distribution with zero mean and so standard deviation 1. Okay. So that is the idea. That is the idea. So we take, so for so arbitrarily selected normal distribution with mean mu and standard deviation sigma. If we take the x minus mu divided by sigma, then it is called the normalization. If we take this equation, then this z is always become a normal distribution with zero mean and standard deviation 1. Okay. So then all the normal distribution can be changed to the standard normal distribution using this equation. So all the normal distribution with parameter mu and sigma can be changed to the standard normal distribution, which has so zero mean and unit variance, unit standard deviation, using this equation. So x is normally distributed and mu and sigma, and standard normal distribution is z, and mean is 0 and standard deviation 1, and we denote that n 0, 1. So then the standard normal distribution has probability density function like it. Okay, so here, so probability density function of standard normal distribution is 1 over square root 2 pi e to the minus z square over 2. And mean is 0 and standard deviation is 1, and you can use the Excel function like this. S is standard. Okay. So then we study the standard normal distribution. And if you have so arbitrarily selected normal distribution mu and sigma, so if x is so normal distribution with parameter mu and sigma, and z is standard normal distribution. So then so general normal distribution is given by mu plus sigma z. Mu plus sigma z. And as you know, that standard normal distribution is given by mu x minus mu. So again, x is I have a mistake. I erase one. So okay, x is general normal distribution mu and sigma, and z is standard normal distribution. So then we know that z can be obtained by x minus mu divided by sigma, and at the same time we know that x is given by mu plus sigma z. Okay, so study the standard normal distribution. If we study the standard normal distribution, then general normal distribution is very so easily obtained by this equation. So instead of study the general normal distribution itself, we study the standard normal distribution and standard normal distribution z, and apply this equation to find the property of normal distribution. So that's why standard normal distribution is very important. Okay. So then, here is standard normal distribution, So, uh, so it is domain is minus infinite to infinite. But the most important thing is minus 3 to 3 because this area covers 99.78% of the whole distribution, and it is cumulative distribution. Okay. So then, first, when we would like to study the Z standard normal distribution, we have to know that the probability that Z is based on, so we would better, if we study the probability that Z is between A and B, so then, so that is all the property of the Z is in this probability. So then we have to calculate integral a to b fx dx, and fx is 1 over square root 2 pi e to the minus 1 over 2 x squared, something like that. So it is so difficult. So we need to study this integral and this complex equation. So to obtain this probability, to calculate the probability that Z is between A and B is that probability of Z is less than B minus probability that Z is less than A. So here is probability density function, and we would like to know this area. So this area is probability that Z is between A and B. So then to calculate this area, we just calculate this area. So here is B, and minus, here is distribution, this area, here is A and B. So we calculate this big area divided by this small, so subtract by this small area. So this big area, and cut this part, out, then we obtain this area in the middle. So to calculate this probability, we just calculate the probability that Z is less than B minus probability that Z is less than A. So then, to know this probability, we only need to calculate this one and this one. Okay? So to know the property of normal distribution, we have to see the appendix C1. Appendix C1 means that okay, so please find your book. And so you may have the 5th edition, whatever it is. So in the end of your book, you have a table. So here, this table is appendix C1, C2, and here, one page before, so here, you have appendix C1, appendix C1. So here is that page. Okay. So we will study appendix, that is appendix C1, and that is appendix C2. So we will study these two appendix so in this slide. Okay, let's go ahead. So if you want to know that appendix C1 is so show that appendix C1 show that so calculate the probability that normal distribution is between 0 and some number. 0 and some number. So probability that 0, z, so some x. So this probability is written in the table. So here, these numbers are all the probability that z is between 0 and some number. So and this number is here. Okay, here is that number. So if you want to, for example, if you want to know that, if you want to know the probability that standard normal distribution is between 0 and 1.96, then you just find this table and let's see. So we would like to know the probability that z is between 0 and 1.96. Then first, here is 1.9. So this number is probability that z is between 0 and 1.90. This number is probability that z is between 0 and 1.91. This number is the probability that z is between 0 and 1.92, and so on. 1.93, 1.94, 1.95, 1.96, 1.96. So then we obtain this number. So 0.4750 is the probability that z is between 0 and 1.96. So this probability is calculated by the integral 0 to 1.96 1 over square root 2 pi e to the minus 1 over 2x dx, x squared dx. We have to calculate this complex integral. Instead of to calculate this complex integral, we just use this table, then we obtain this probability. So this calculation, this integral calculation is so difficult, so that is not your job. It is mathematician's job. So mathematicians already study this property, this integral, and write the result on this table. So we need not to calculate this probability by ourselves. Instead of using this complex integral, we just use this table. Okay, then we can obtain the probability. Okay, so here. Okay, and so if you want to know the probability that z is larger than 1.96, so then because this half, I'm sorry, so positive half of positive half of the distribution is, I'm sorry. So positive half of this distribution is 1 over 2, 0.500. So this area, so probability that z is greater than 1.96. So this area is probability that z is greater than 1.96. So to obtain this area, we just consider that so this total value of this half bell shape is 0.5, and this area from 0 to 1.96 is 0.4750. So this remaining area in the right tail is this number, so 1 over 2 minus, so this number, so 1 over 2 minus 0.4750, and finally we obtain that 0.0250. So this area is 0.0250. This area is 0.0250. And another example, if you want to know that the probability that z is between minus 1.96 to plus 1.96, so then because the normal distribution is symmetric, so that means probability that z is less than x is the same as probability that z is greater than minus, I'm sorry. So the symmetric means that it is same, but because of symmetric, we will use the property that z is between 0 and x is the same as probability that z is less than 0, greater than minus x. So it is these two probability is same, and on the other hand, probability that z is less than x is the same as probability that z is greater than minus x. So it is also the same because the distribution is symmetric. So we would like to know that probability between minus 1.96 to plus 1.96. Here is minus 1.96 plus 1.96. We would like to know the area between minus 1.96 to plus 1.96, so this area. And since we know that from 0 to 1.996, so probability that z is between 0 and 1.96 is equal to 0.4750. So left half of this area is also 4750 because they are symmetric. So we sum up this number and this number, then we obtain this probability. So finally we obtain that. So probability that z is between minus 1.96 plus 1.96 is that. So probability that z is between minus 1.96 to 0. Probability that z is between 0 and 1.96. And this probability is one and the same because of this property. So it is 0.475 and 0.475, and finally we obtain that 95%. Okay. So we apply this idea then. So minus 1 to 1, the probability that between minus 1 to 1 covers that 68.26%. And minus 2 to 2 covers that 95.44%. And minus 3 to 3 covers that 99.73%, which is empirical rule we've studied in previous chapter. Please find chapter 4. So then you can find the empirical rule. So then you can find this property. Okay, so probability that z is between -1 to 1, then it is 2 times probability that z is between 0 and 1 because it is symmetric. So normal distribution is symmetric. So we find as 68. -2 to 2 is 95. -3 to 3 is 99. So how can we know this point for 772? So we can use the appendix C1. So I've saved appendix C1 in my Word file. I will share it in Blackboard. So it is it is appendix C2. So I will discuss it later. I'm sorry. So appendix C2. So in the last page of your textbook, you have appendix C2, which is the cumulative normal area. So in this table, so here is the appendix. It is appendix C1, appendix C2. So I will show you the appendix C2. So here is appendix C2. That is appendix C2 in the last page of your textbook. So in this page, you can find this equation. So this table, this appendix C2 table, calculate that probability that z is less than x. So, for example, if you want to calculate the probability that z is less than 1.96 or probability that z is less than minus 1.96, so you find this table and minus 1.9 is here, so can you see it? Okay. Okay. I'm sorry. So here is 1.9 and 1.90, 1.91, 1.92, 1.93, 4, 5, 6, 1.96. Minus 1.96 has value 0.0250. So probability that z is less than minus 1.96 is 0.0250. And probability that z is plus 1.96. Let's see. So instead of minus 1.96, let's go to the plus 1.96. 1.9. So 1.9, 1.90, 1.91, 2, 3, 4, 5, 6. 1.9, 1.96 is here. So 0.9750, 0.9750 is that probability z is less than 1.96. So probability that z is less than plus 1.96 is 0.9750. So the probability that z is between minus 1.96 to 1.96 is probability that z is less than minus plus 1.96 minus probability that z is less than minus 1.96. And finally, we obtain this result. Okay. So then using the appendix C2, we can calculate the normal distribution. So that is illustration. So we would like to know this area of this bell shape, a part of this bell shape. So to do that, we calculate this area and this area. So that is probability that z is less than plus 1.96. And this area is that probability that z is less than minus 1.96. So then we cut here and remove that out. So then we obtain this area of this shape. So that is probability that z is less than 1.96 minus probability that z is less than minus 1.96. So this number is, and finally this 0.9750 minus 0.0250, and it becomes 0.9500, as we discussed in the previous page here. So we obtained the 95%. Okay, and appendix C1 and appendix C2 are all very useful, and you'd better know that how can you use the C1 and C2. Okay. So the important value is 2.33. So 2.33. So this number is 2.33. So this area covers that 49.101, and this area is almost 1%. Okay, so 2.33 is very important value. So there is some important value for z. So probability, so this part is probability that z is greater than this small z. Small z. Okay. So again, this area is probability that z is greater than small z. Okay, and small z is here. So this small z is 0.675, then this right tail area is 25%. 1 to 82, then right tail becomes 10%. 1.645, then 5%. 1.960, then 2.5%. And 2.326, then 1%, and so on. So this critical values and this right tail area is very important, so you would better keep these values in mind. And the middle area, so minus z to z, so that means that probability that the normal distribution, standard normal distribution is between minus small z to plus small z. So if small z is 0.675, then this area is 50% of the total area. And the small z is minus 645, then it covers 90%. So this 90% means that probability that large z is between minus 1.645 to plus 1.645. So then we have this value. This probability is 90%. 9%. Okay. So please keep in mind this critical point and this middle area and tail areas. It will be used when you study the confidence interval. So let's use this table using this example. John took an economic exam and he scored 86 point. And the exam score, class exam score has mean 75 and standard deviation is 7. We assume that, so X is John's score, and exam score, so economic exam score, and this exam score follow the normal distribution with 75 mean and 7 standard deviation. So, and John's score is 86. So then first we normalize. So what is the percentile of John? So the percentile which is in the John included. So then let's calculate the z-score. They say that it is normalization or z-score. Z-score of John's exam. So 86 minus 75, it is mean. So mean says that mean is 75. Divided by 7, standard deviation, 7. So then we obtain the z-score 1.57 for John's score. So then John's score is 1.57 standard value. So then probability that X is less than 86 is that probability X minus 75 divided by 7 is less than 86 minus 75 divided by 7. So that is probability that Z is less than 1.57. So this probability and this probability is one and the same. I'm sorry. So probability of X is less than 86 is the same as probability that Z is less than 1.57. And 1.57, so probability that Z is less than 1.57 is 84.18%. So in this case, we have to use the appendix. Okay. So minus 1, plus 1.5. 1.50, 1.51, 1.52, 3, 4, 5, 7. 5, 6, 7. So here, this is 1.57 probability that Z is less than 1.57. So 0.9418. So 0.9418 when Z is 1.57. So this area is 94.18%. Okay. So the probability that X is less than 86 is that the same as probability that Z is less than 1.57, and it is 0.94818. Okay. So John is approximately in the 95th percentile. So we can use the normal distribution in this method. Okay. So then next question is that what is the probability that randomly chosen test taker would have a score at least 65. So then probability that randomly selected exam taker has a value score less than 65. Okay? So then this probability is the same as that x minus mu divided by sigma, so which is 65 minus 75 divided by sigma 7, so this number. So that is z-score, so probability that standardized normalized value is less than minus 1.43, so this number. And using the C2 or C1, we can so calculate that this area is so if we use the C1, then the probability that z is less than or equal to minus 1.43 is that probability that at least 65, I'm sorry. So we have to calculate this one. Okay, again. We have to calculate the probability that x is greater than 65. So then that is the same as that probability that x mu minus mu divided by sigma is greater than 65 minus 75 divided by 7. So that is probability that it is z is greater than or equal to minus 1.43. So this area, we have to calculate this area. So using appendix C1, so it is this area is same as probability that z is between 0 and minus 1.43. So this area, and this area is always 1 over 2 because it is half of the bell shape. So it is always 1 over 2, 0.5. And this one, the probability that minus 1.43 z 0 is the same as probability that z is 1.43, less than 1.43 and greater than 0. So we can use the appendix C1, we obtain this number, and finally we obtain this number. Okay. If we use the appendix C2, then we directly know that this area, so probability that z is greater than minus 1.43, so this probability is 1 minus probability that z is less than 1.43, and z is less than 1.43 is obtained by this appendix C2. So minus 1.43. So then here minus 1.40123. So then 0.0764. 0.0764, and we obtain that 0.9236. Okay? So we can calculate this probability. Okay. So using Excel, this area can be calculated by this syntax. So for example, mean and variance is 70 and 7. Mean is 75 and variance is 7, and this x is 80. Then we just say that norm norm.dist and 80, x is 80, and mean and standard deviation, mean 75, standard deviation 7, and 1 means that it is cumulative distribution, this area. So then we obtain this number. Okay. So using Excel, we need not to use the appendix C1 or appendix C2. We can directly calculate the normal distribution. So please keep in mind the normal distribution. So if you want to calculate this probability, so and the mean and variance, mean is 0.2040 and standard deviation is 0.001. So then the probability that the diameter between these two numbers, so then we have to calculate this equation. So then this probability can be calculated by that probability x is less than 2.042 and minus probability that x is less than 2.039. So then we just use the normal function, normal distribution function, and we obtain this number. Okay, so we can check this result using the appendix C2, so then we can obtain this number. So okay. So mean is 2.04 and the standard deviation was, this mu is 2.7 and standard deviation was 0.001. So then probability that x is less than 2.039 and we have to know that probability that x is less than 2.042. So then we can obtain this value using normal distribution and 2.039 comma mu comma sigma comma 1. So then we have this number. And this probability is normal distribution 2.042 comma mean comma standard deviation and cumulative distribution. So then probability that 2.039 x 2.042, so probability that x is between these two values is this number minus this number. So then we obtain 81.85%, which is the same as shown in this table, in this slide. Okay, so then using the Excel, we can calculate the probability of normal distributions. Okay. Inverse normal is a little difficult, so we would better not discuss it in this semester. Okay, so that's it for the chapter 7 normal distribution. So let's keep in mind the normal distribution is most important continuous random distribution for the continuous random variable. Okay, we will use the normal distribution in chapter 8 and 9, and it will be very important. So please repeat this chapter again and again and understand what is the normal distribution. Thank you so much and see you next chapter.